Mars has had a busy year on the question of whether it may have once hosted life, especially with the recent findings of structures and sedimentary rock from a formation in the Godier crater on Mars known as Chevea Falls. This formation is basically a dry riverbed, and the rock inside it is sedimentary, meaning it was laid down by water. Sedimentary rock is where you find fossils on Earth, so this type of rock has always been of great interest in the exploration of Mars. Here they found basically every chemical necessary to support microbial metabolism. If there ever was microbial life on Mars, it had plenty of food. That does not mean that life was there, however. However, the Chevea Falls sample was studied further by taking a core sample from it, known as the Sapphire Canyon sample, and the scientists noticed what they are calling leopard spots in the sedimentary rock that look suspiciously like similar structures found here on Earth that are explicitly related to life on Earth. Basically, these structures are formed in reactions involving hematite, which is a free energy source for microbial life. Within these spots are the minerals vivianite and greigite. These minerals on Earth are found where something decomposes. In fact, it's found in peat bogs as a product of decomposition. That does not unequivocally mean that life was involved, rather it gives the appearance of life, having been involved in the formation of those minerals. But it's important to remember that there may be other ways for this to happen without life. It's just not clear how it would happen without life in this sample. The rest of the analysis of the sample basically precludes everything we know of as far as non-life ways this could happen. Though it's science, someone may yet think of a new way for that chemistry to occur. But amid all that, there were other indicators of something going on at Mars that did not make headlines as big as the leopard spots. In March of last year, another analysis from the Curiosity rover at Gale Crater found some rather strange organic chemistry. They found decane, undecane, and dodecane, which are all large organic compounds that look like they could be the remains of fatty acids inside the mudstone sedimentary rock at Gale Crater. That's a different crater and rover than the leopard spots. So if Mars had life, and this is indeed evidence of it, it had widespread life. Unfortunately, however, there are non-biological ways to create these organic compounds. So again, it does not immediately implicate life, it merely hints at it. But coming out of that story is something that might get us close to being able to say there was once life on Mars. After that work was done, it led to another study. So organic compounds like this can be delivered by meteorites. Some types of meteorites are loaded with all sorts of advanced organic chemistry that happens without life, but is linked to life. To the point that one hypothesis for where Earth got the materials for life are the asteroids and comets. But therein is a clue. We know the numbers on just how much organic chemistry of this nature would be present from non-biological sources. It turns out the abundances are too high for non-biological sources, which leaves life as the culprit. It doesn't prove it, but it does make it reasonable to put life on the table. And it has to be said, unless a mistake was made in this study, it's the only option standing right now. So how this was done was a series of radiation experiments and modeling that take the Curiosity dataset here and reconstruct its last 80 million years for this sample, which is the amount of time this particular rock was exposed on the surface of Mars. That lets you estimate how much organic material was present in the sample before its exposure to the radiation environment of an exposed surface on Mars, which destroys organic material. It doesn't match, not by a long shot. There's too much organic material left in the sample for a non-biological origin. However, the reason this can't yet be called anything but a hypothesis based on odd evidence is because experiments still need to be done to determine how quickly organics break down in Mars's specific geology and the general conditions of Mars, which may require more observation by the rovers specific to the goal of trying to nail down those precise conditions. But once that happens, if this finding still stands, it's yet another piece of increasingly strong evidence that some kind of life once existed on Mars. If so, then we move to the next question, which is where did that life come from? Was it Earth life that was transported? was Earth life transported from Mars? In which case, Mars is actually our homeworld, not Earth. Is it evidence of true alien life, totally unrelated to Earth? All three of those questions have far-reaching implications, but the only way to know or even begin to try to figure out the answer is a sample return mission, which is not currently on NASA's plate. It may well be China that returns the first samples and answers the questions. In the meantime, the Curiosity rover is on the hunt for more organics actively right now. Observations are being done to get more data on the organic chemistry of Mars, so expect further surprises to come later this year. That will also further help constrain down why the disparity in the amount of organics exists, and if it does indeed point to life having once been in the waters of Mars. But that leads to another new finding. In regards to the distribution and prevalence that life on Mars might have had if it existed, there is also new information, not from the rovers, but the Mars orbiters. It's long been known that Mars had liquid water oceans, but what wasn't clear was how widespread these oceans were. In short, how blue was Mars? And it turns out 3 billion years ago, Mars was very blue indeed. In fact, there's even recently uncovered evidence that the largest canyon in the solar system, Valles Marineris on Mars, was once extensively wet. It had water in it, but it was not formed by water like you'd normally think for a canyon. What actually formed Valles Marineris isn't well understood, but it seems basically to be a product of Mars cracking at some point due to shifting volcanism earlier in its history. It's basically a stress fracture, which must have looked spectacular as it formed. Near Valles Marineris, however, researchers at the University of Bern and others looked through high-resolution imagery of the area and found structures near the canyon that appear to be old river deltas, meaning the mouth of a river where it meets the ocean. That started setting boundaries on where and how extensive Mars's oceans were, at least at their height before that planet lost them gradually. What this did was help constrain down how large that ocean was overall, and the answer is that it had to be at least the size of the Arctic Ocean on Earth. It also proves once and for all, reasonably, that Mars did indeed have extensive oceans, though there was only a little doubt on that count left in the scientific community. It would have stretched across the northern hemisphere of Mars. If that ocean teemed with life, then that life would have been as extensive as it is on Earth. Microbes pervade the oceans on Earth, and probably would have done so on Mars. It also adds further evidence to a rather disturbing reality. So Venus, Earth, and Mars are all thought to have been surface water worlds early on. Only one still is, Earth, and that seems to indicate that Earth-like water worlds are not rare in the universe, but they are apparently very transient and very finicky. This may actually be a Fermi paradox solution in itself, or at least one to think about. Water worlds the size of terrestrial planets in the same class as Earth may not simply last long enough in most cases to spawn civilizations before they dry up and become uninhabitable. And that leads to another recent but oddly interesting discovery regarding Mars. It turns out Mars affects Earth's climate. So the planets all tug on each other gravitationally, which causes cyclic variations in Earth's orbit and tilt, which affects the amount of sunlight it receives, which can warm and cool the planet overall. These cycles are called Milankovitch cycles, and the huge effect of those are the ice ages. The cycles are crucial to understanding how and when ice ages occur. But ice ages are really groups of events. We tend to think of it in terms of the last ice age, and it was. But overall, we are still in an ice age in the broader sense and have been for 2.6 million years. Indeed, Homo sapiens has never known a time that wasn't during an ice age period. And in fact, the once enormous Laurentide ice sheet still exists as remnants, though they are actively melting to this day. In this broader sense, Earth has seen at least 5 major ice age groups over its history, probably more, and the Milankovitch cycles are driven largely by the planets. One major one that takes 430,000 years to complete is due to Venus and Jupiter collectively tugging. And what it does is causes Earth's orbit to go from circular to more elongated, and then it returns back to circular. That change in sunlight, exposure, and temperature causes the ice sheets to advance and retreat. The question was, what role did Mars play in this? It was always assumed that Mars was simply too small to be much of a factor in these cycles, but that assumption was apparently wrong. Recent modeling showed that when Mars was removed from the model, 2 of the cycles disappeared, one cycle being a 100,000-year cycle and the other a 2.3 million-year cycle. Yet when the researchers increased the mass of Mars in the computer modeling, the same cycle shortened because Mars was having a greater gravitational effect. Weirdly, the model also showed that Mars had a measurable effect on Earth's tilt. That's complicated, because the Moon serves to regulate the tilt. But there is still a variation over time, and when they increased the mass of Mars in the computer model, Earth's tilt level actually went down, which in turn means that Earth's tilt is also being stabilized to a degree by Mars as well as the Moon. This is weird stuff because Earth's habitability is pretty tight in some ways, so much so leading to the rare Earth hypothesis. But this shows that even worlds like Mars that were thought to not have much of an effect actually do. That could be bad news for rare Earth, or it could reinforce it, and we might want to broaden the idea out and call it the rare solar system hypothesis. But not a lot of work has been done here on alternative arrangements of planets and moons that could result in the same thing, or some other set of conditions that allows for surface life. Or even if Earth is ideal, there is such a thing as the idea of an exoplanet that is better than Earth. Hiding in here, though, is perhaps a greater question for humanity. So ice ages have profoundly shaped evolution on Earth. When the glaciers advance, the forests and grasslands shrink. And that seems to have played a role in the evolution of walking upright, the necessity for tool use, and how that was an advantage, and very possibly how humans and many other animals, but many notably not, became social. If Mars had not been there, would we be here? Thanks for listening. I am futurist and science fiction author John Michael Godier, currently eyeing the solar system suspiciously, as though I am ever not doing that. Someone has to do it after all. But all of this just goes to show how ridiculously complicated the various factors are to create a situation like Earth has, and we still don't even know all of them. Now it turns out, we need Mars hanging around out there, lollygagging and carrying on with Jupiter and Venus to keep the lights on here. I won't even get into my long list of grievances I have for the sun and its gravity. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.